Alright, so in the last couple of videos we looked at singly linked lists, and now we're going to look at a double linked list or a doubly linked list. With a doubly linked list we have nodes, we have a head, we have a tail, and each node in the list points to the next item in the list and to the previous item in the list. And so this time we have two reference fields. This would be the next field and this would be the previous field. And as you can see, for the first item in the list, the previous field will point to null, and the last item in the list, the next field will point to null, just like it does with singly linked lists. And so as I said, this time we have references to the head and the tail. So in this list, Jane would be the head node and Mike would be the tail node. And so we can traverse the list from front to back, from front to tail, or from tail to head. And this time, if we want to insert or remove a node from the end of the list, we can do it in constant time because we have a pointer or a reference to the tail of the list. And so the advantage of using a doubly linked list is you can work with the node at the front of the list or the node at the end of the list in constant time. But if you want to work with nodes in the middle of the list, you're going to have the same problem that a singly linked list had. You're going to have to traverse from the head or from the tail, find the node you want to work with, and in the worst case, that could be a linear operation. So let's look at inserting and deleting nodes into a doubly linked list. So we have a little more work to do now because we have two references that we have to manage, the next and the previous. And so if we wanted to insert Bill at the head, we'd start out the same way that we did for inserting a node in a singly linked list. We're going to create a new node for the new information. And now we need to set Bill's next and previous field. So his next field is going to be whatever is currently being pointed to by head. So this is the same as when we did singly linked lists. And his previous field is going to point to whatever Jane's previous field is, because if we're inserting Bill in front of Jane, which is what we're doing, then Jane's previous field is now going to become Bill, and Bill's previous field will become whatever Jane was pointing to. Now, if we're always inserting at the head, that would mean that Bill's previous field is going to point to null. And now we have to fix Jane's previous field because Bill is being inserted in front of her. And so we want her previous field to now point to Bill. And then we're going to assign the head field to Bill because Bill becomes the new node that's at the front of the list. And so essentially, when we insert a node, it's all about setting the references of the node we're inserting and also updating the previous field of the current head node. And so after we've done all of that, this is what the list will look like. So we didn't have to change Jane's next field because when we're inserting in front of the list, what comes after Jane isn't going to change. We had to update the previous field because the previous field would have been pointing to null, but now it's going to point to the new node. Because if this previous field used to point here, we're dropping a node in front of it, and so we need to update the previous field. And so we need to update Bill's previous field to point to whatever Jane's previous field was pointing to. And then on the final step, we just set the head to Bill. We go through the same steps if we were to insert Bill somewhere else. In that case, we'd have more references to update, but we'd go through a bunch of similar steps. We basically would have to set Bill's previous and next, and then we'd have to update the next field of the node in front and the previous field of the node that comes after the one we inserted. But as I said, when you're working with linked lists, you mainly want to be focusing on working with items that are at the front of the list, or in the case of doubly linked list, at the tail of the list. If you start playing around with items in the middle, you're going to lose the advantage of a linked list, which is that inserting and deleting items from the front. And in the case of a doubly linked list from the end, you can do that in constant time. Once you start playing with other nodes, you're getting up into potentially linear time. Okay, so that's inserting a node at the head. So let's go back to our original list just to remind ourselves of what it looked like. So we're back to before we inserted Bill now, and we're going to insert at the tail. So once again, if we want to insert Bill at the tail, we'll create a new node called Bill. And we want to assign the tail's next field to Bill's next field. Because if we go back to the previous slide, if we're going to drop Bill in here, then whatever this guy is currently pointing to as next, we're going to want Bill to point to as next. And so we're going to assign the current tail's next field to Bill's next field. We're going to assign whatever the current tail to Bill's previous field, because Mike is currently the tail. And so if we put Bill in here, we're going to want Bill's previous field to point to Mike. So we want to point the previous field to the current tail. And then we're going to want to assign the tail's next field to Bill. And so Mike is the current tail, and after the insertion, his next field, we want him to point to Bill. And finally, we're going to assign the tail to Bill. And we can do that in constant time complexity. It doesn't matter how many items are in the list. You're going to go through the same number of steps to insert a new item at the tail. And so after the insertion, this is the situation we'll have. So Mike's next field has been updated to Bill. Bill's previous field has been set to Mike, and his next field has been set to null, which is what Mike's next field used to be. And the tail has now been set to Bill. So let's say we want to delete from the head of the list. So we want to delete Jane. Well, let's look first at what we'd have to do. Well, we're going to assign Jane to a remove node, and then we want to assign John's previous field to whatever Jane's previous field is pointing at, because we're removing her. So we want to take that reference and go here, and then we just need to move the head reference to John, and that effectively removes Jane from the list. So we're going to assign Jane to remove node. We're going to assign John's previous field to Jane's previous field. We're going to assign head to whatever's at Jane's next field, because Jane's next field is pointing to John, so we're going to assign John to head. And then we're going to return remove node from the method, and if we wanted to, we could clean up Jane's next field by setting it to null. We don't have to, but we could. And once again, that'll be constant time complexity. And so once we've gone through that, Jane will be gone, and John will be the new head of the list. So let's put Jane back in, and let's look at removing the tail instead. So this time we're going to remove Bill. And so how would we do that? Well, we're going to want to take Mike's next field and point it to null. And we're going to want to move the tail to Mike. So the tail will be moved to the current tail's previous node. And so we'll assign Bill to remove node. We'll assign Mike's next field to Bill's next field. We'll assign the tail to Bill's previous field, which is Mike. And then we'll return remove node from the method. And once again, we can do this in constant time. It doesn't matter how many items are in the list. If we want to delete an item from the tail, we can do it using the same number of steps. And so after the deletion, we'll have this situation where Mike is now the tail and Bill is gone. So in general, to insert a node A between nodes B and C, we want to plop A between B and C. We're going to assign A's next field to B's next field, because B's next field will be pointing to C, and we're going to put A between them. So we want A's next field to point to C. We're going to assign A's previous field to C's previous field, because C's previous field will be B. And we want A, we're going to drop A in between them. So we're going to want A's previous field to be B. And then we assign B's next field to A and C's previous field to A. Now, to do those 4 steps is constant time, but unless we're doing this at the beginning or the end of the list, we have to find nodes B and C first, and we're going to have to traverse the list to do that. And so the worst case for this is actually linear time, O to the n. Now, to remove a node A from between B and C, so this time we have nodes B followed by A followed by C, we assign A to remove node. We want C's previous field to now point to B, because we're removing A, so we'll assign C's previous field to A's previous field, because A's previous field is pointing to B. We want B's next field to point to C, so we'll assign B's next field with whatever A's next field is pointing at, because A's next field is currently pointing to C, because it's in between them. And then we just return A from the method. Once again, these steps are constant time, but we have to find A first in the list. So unless A is at the head or the tail, we're going to have to find it. And so the worst case for this would actually be linear time. And that's it for looking at how doubly linked lists work. Once again, we're going to do a simple implementation of a doubly linked list. We're going to update our singly linked list implementation to turn it into a doubly linked list. So let's go ahead and do that. I'll see you in the next video.